So in example 2 on page 104, we're going to look more formally at this same example that we already saw in example 1. We want to prove that the series that we saw in example 1 converges. And just like in the previous section, let's write down our scratch work first. So, what's our scratch work? Well, this series is an alternating series. So let's write that down in a way that we really can convince someone that this is true. So we have minus 1 to the n minus 1 over n. And if we write it in a way where we are pulling out that minus 1 to the n minus 1, that is the part that's alternating. And then we have still the 1 over n. We can now really see that this is an alternating series. And we can write down what Bn is. Bn from the theorem that we saw in the previous video. So Bn is 1 over n. So by rewriting the series in this way, we can really see that A, it's alternating, and B, that this Bn is equal to 1 over n. So then, to be able to use the alternating series test, we have to show that the two conditions are satisfied. We already talked about it, but let's write it down one more time. So the limit as n goes to infinity of 1 over n, that has to be 0, and that's true. As n goes to infinity, 1 over n goes to 0, so this is true. And then the second condition was to compare successive terms. So comparing 1 over n plus 1 with 1 over n. And it's true, 1 over n plus 1 is always a little bit smaller than 1 over n, no matter what value n takes on, as long as n is positive. And in our case, of course, n is positive because it goes from 1 to infinity. So this is also true. Okay, this is our scratch work. Now we are ready to write our proof. And writing our proof just means to put words around our scratch work. So what do we have? Since the limit as n goes to infinity of 1 over n is equal to 0, and 1 over n plus 1 is less or equal to 1 over n for all n, the given series converges by the alternating series test. By the alternating series test. And that's it. That is our proof. So if you go back to the theorem said that if you have an alternating series and both conditions A and B are met, then the series converges by the alternating series test. So those are the three things that we have to cover. We have an alternating series, condition A is met, condition B is met, therefore we can conclude that the series converges. Okay, in part B, they ask us to use the first 4 terms of the approximation to use the first 4 terms to approximate the value of this infinite sum. And then they want to know what is the maximum possible error of this approximation. Okay, let's see. So we have our series, n goes from 1 to infinity, of minus 1 to the n minus 1 over n, and this is 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6, and so on. We only want to look at the first 4 terms for our approximation. So this is 1 minus 1/2 plus 1/3 minus 1/4. And if you plug that into your calculator, you get a value of approximately 0.583 as our value. So this is our approximation. And now the question is, how good is this approximation? And for that, you can look back at the alternating series estimation, and that says that if you use the first 4 terms, then the 5th term is an overestimate for your error. So whatever your error is, it's less than 1/5. And so this is like an upper bound for the error of the approximation. And so we can write down our conclusion. So the approximate sum of the series is 0.583. And by the alternating series estimation theorem, we know that the maximum error in this approximation is given by B5, which is 1/5, or 0.2. So let's write that down too. By the alternating series estimation theorem, we know that the maximum error in this approximation is given by